Okay. Yes. So thanks. So as we said last time on Tuesday, so I gave a general the general setting of algebraic quantum field theory, in which the main tenet is the fact that everything should be fixed by the knowledge of the net of observable algebras. And as I also said on Tuesday, this raises immediately some questions. In particular, this raises the question of where are charged states of the theory. So because the observables create from the vacuum only neutral states. So one asks, it is natural to ask how one can recover from the knowledge of the observables only for the knowledge of the observables only the charged states, and then of course the charged fields. So in the observable algebra there are only things that commute at space-like distances, but one is used to have also Fermi fields, and so one asks where are those all those structures which are familiar from the usual field theoretical approach. And so the main observation is that if we insist on the fact that only observables should fix the theory, one this also implies that the net should not have internal symmetries, uh, because this is something more with respect to the knowledge of the observables. So this means that all the symmetries of the theory should be gauge symmetries, which don't act on the observable. So if you only know the observables, you don't see gauge symmetries. And if you have gauge symmetries, you usually have superselection sectors. So you usually have that the Hilbert space is decomposed in a direct sum of spaces in which the superposition principle holds, but it doesn't hold if you take two vectors from two different superselection sectors. And so this suggests what is the answer. The answer is that one gets, as we saw in the Dirac field case, these superselection sectors give different inequivalent representations of the observable net. So one expects that this is a general situation, that once you know the observable net, you can recover charged states and unobservable fields from the knowledge of for the analysis of the representations of the observable net. This is actually a general. So what we saw in the Dirac field case is rather general. There is this theorem which was proven by Doppler, and Roberts in '69, in which they start from not from the observable algebras, but from a field algebra. So they assume that there exists a net of field algebras. So this is just a net. They don't assume any commutation relation on this for this net. They assume that there exists a representation. This lives on a Hilbert space. They assume that there is a representation on this Hilbert space of a compact group. And they assume that the observables are the fixed points under the action of this group of the fields. So these are the elements of the field net which are left invariant by the action of the field. But plus some other hypotheses, so clustering, for the vacuum, and Schiller property also. So they start from the assumption that there is some field net from which you can select the observables as fixed points under the action of the loop. And moreover, they assume that these two nets are relatively local one to the other. So A01 commutes with A02 if O1 is space-like to O2. These are the only commutations relations that they assume. In this situation, they obtain that the Hilbert space is decomposed in a sum of superselection sectors. And the representation, the defining representation of this decomposition is the decomposition of the representation of the gauge group in reducible subrepresentations with some multiplicities. And the representation pi of the algebra of observables, which is defined by the field net, is also decomposed along this orthogonal direct sum decomposition with some multiplicities. Here the xi are positive, are natural numbers. And moreover, the two pi xi prime are inequivalent. These are irreducible representations. They are inequivalent, but they become equivalent in restriction to the space-like complement of any bounded region. So pi xi restricted to A O prime is unitarily equivalent to pi xi prime restricted to A O prime for all O prime. Which has, of course, the physical interpretation that these representations describe charges which are localized in some bounded region. So they describe situations in which you perturb the vacuum only in some bounded region, and nothing happens at a space like infinity. So this suggests that one should look. So if one only starts from observable, this suggests that one should look at representation that behave like the vacuum in at space like infinity, like those ones. So you can at this point you can reverse the point of view. One starts from the observables. One forgets about the existence of the field net. One starts from the observables and tries to recover all this structure only from the knowledge of the observables and from their representations. Okay. So of course one has to select a useful class of representations, because one expects that the observable algebra has also other representations that don't describe few particles in the vacuum, but so it could have representation that describe situation in which you have a uniform distribution of matter going to infinity. So one needs to select a particular class of representation which are of interest in quantum field theory. So in which you only perturb the vacuum in some with some particles, and so one needs a selection criterion for this representation, and one candidate, of course, is this criterion. So which is was called the DHR selection criterion. One says that pi is a irreducible representation of A is DHR if that happens. So if pi restricted to A over prime is unitarily equivalent to pi naught, which is the vacuum representation of the observable net, for all double cones, for instance. And this is the vacuum representation. This is a possible selection criterion, which is suggested by the theorem. But so one has to be careful. If one thinks over it just 1 minute, one realizes that representation cannot describe electric charges, because for an electric charge you can always measure the charge on a very large sphere at space like infinity, essentially, because of Gauss law. If you have a charge here, you can measure the electric flux on a big sphere, and so you don't expect that the representation pi, which describes an electric charge, will satisfy this relation. So one expects that this kind of representation only describes charges which are massive. So only describe only describe charges in massive theories, in which you don't have massless particles which can let you measure the charge in some a space like infinity. And in the previous theorem, that was reflected by the assumption that you had clustering for the vacuum. That assumption of clustering is essentially the same as saying that the theory is massive. Anyway, that's a starting point. Yes.
This theorem does not apply in general to gauge theories, let's say, because in there I have like charges with strings, so they are not localized inside
That's the other limitation, but okay, we will discuss this other situation. So when this was invented, that concept of string was probably not very popular. So at that time, people tended to believe that this was okay for any massive theories. Instead, at some point, it was realized that even if the theory is fully massive, you could have, so for instance, in an abelian gauge theory, you could have that kind of charges, and so you have to refine this criterion, and this can be done. I will discuss this afterwards. But since the structure is simpler in this situation, I will mainly focus on this, and will say just something about the generalizations, which are so technically more complicated, but conceptually are the same. Okay, so for the moment, we look at those representations, and so what one wants to do, one wants to show that this set of representation has the same structure as the set of charges of quantum field theory. So what can you do when you have charges? You can compose charges. So and you can analyze when you compose charges. You can describe their statistics. So you can analyze what happens when you exchange charges. So the localization of charges. The aim of this analysis is to show that the set of those representations has the same properties. So one has to construct to show that you can have the same structures in the set of representation. And in order to do this, the main observation is that one can pass from generic representations to endomorphisms of the quasi-local algebra, by simply saying that I can take for each double cone O, I can take a unitary operator such that pi A is VO pi 0 A VO star, where where A is localized in AO prime. And I can define rho of A as VOA, VO star for all A in A. And sorry. Sorry, this is the other way around. This way. So VO is a unitary from the vacuum Hilbert space to the Hilbert space of the representation. And in this way, I get something in the Hilbert space of the representation. And this has the property that if A is localized in O prime, then rho A is equal to A. Now I suppress pi 0. And moreover, if one assumes Hug duality, which is the requirement that A of O is equal to A of O prime prime, which means that the local algebras are maximal with respect to locality. Of course, you always have the inclusion here, and actuality is the assumption that they coincide. So the local algebras have to be maximal. Everything which commutes with O prime is already in O. So we take this assumption, and this shows that rho maps A into A, because if I take I take some A in some region O1, I have O is the region of localization of rho. There is some O1 here in which A is localized. And then I can take O2, which is a double cone which contains both double cones. And I can take a B, which is in O2 prime. Then since B is contained here, B is equal to rho B. Because of localization. But then rho is a representation, so it is multiplicative. Then A and B commute because B is here and A is here, and they are space-like separated. And this is again B. This means rho of A is in the commutant of O2 prime, but by duality this is AO2, which is inside A. So any local element of A is mapped inside A, and then since A is the norm closure of the local algebras, this continues to hold for all elements of A. Yes.
Why does B and A commute? Since
because A is localized. A is localized here and B is localized here.
Yes, yes. I was thinking that B was localized in O2.
No, it's. So using locality and actuality, one gets that rho is an endomorphism. Yes.
So when you write VO star A VO, you are like you are identifying A
with pi naught of A. Yes. So pi naught is the vacuum representation, so it's the defining representation of the algebra. So these rows are called localizable endomorphisms of A. They are endomorphisms, they map A into A, and they are localizable in this sense. And moreover, they are also transportable, which means that if you have for any other region, rho is transportable. This means that for any other O1, there exists a rho 1 which is equivalent to rho. Because the DHR representation can be localized in any double cone. So instead of taking VO, I take VO1 and I get another one which is equivalent. And let me indicate by delta the set of localizable transportable endomorphisms. I get this set of morphisms. And then I have intertwiners between morphisms. The set of intertwiners between two morphisms is denoted by rho sigma, and is the set of operators T in B of H naught, such that T rho A equals sigma AT for any A. And by the same argument, like an argument similar to that one has that if I have rho here in O1, here is the region of localization of rho, and here is the region of localization of sigma for any bigger double cone which contains both rho, the intertwiners rho sigma are contained in A of X by an argument similar to that. So also intertwiners are contained into the algebra. So I was saying why is useful to pass from so for any DHR representation you have a set of localizable endomorphism, and the usefulness of this is that you can compose morphism while you cannot compose representation because they go to different Hilbert spaces. You can compose morphisms. So given two localizable and transportable morphisms, I can do the composition. I can give me rho and sigma. I can take rho sigma, which is also localizable and transportable. So it's easy to see. And moreover, if rho is equivalent to rho 1 and sigma is equivalent to sigma 1, then rho sigma is equivalent to rho 1 sigma 1. So this is actually a composition of classes, of unitary equivalence classes of morphisms. And then one also has operations on intertwiners. The first operation is obvious. If I have T in rho sigma and S in sigma tau, then the product T ST is an intertwiner between rho and tau. But then, this has nothing to do with composition of morphism. This could you also have with representations. It doesn't matter that you have morphisms, but instead the fact that you have morphisms give you another operation on the intertwiners, which is the following: if I have T in rho sigma, in rho tilde, and S in sigma tilde, I can form okay, I can form the product T cross S, which is by definition T of rho S, P times rho S. And this is an intertwiner between the products, rho sigma, rho tilde, sigma tilde. It's simple computation. You verify that is an intertwiner between rho sigma and rho tilde, sigma tilde. So this means that delta, the set of localizable and transportable morphisms, has the structure of a tensor symmetric tensor category. So you have the objects are the morphisms, the intertwiners are the arrows are the intertwiners, but then you have a product of objects and a product of intertwiners which satisfy all the axioms. So this is a strict is a symmetric monoidal category. And moreover, we have locality, and locality also gives some properties to these two products, the products of intertwiners and the products of this product of intertwiners and this product of morphisms. So lemma. First, first statement: if rho 1 is localized in O1 and rho 2 is localized in O2, delta O1 are the morphisms which are localized in O1. And O1 and O2 are space-like separated. Then rho 1, rho 2 is equal to rho 2, rho 1. The composition is commutative if the two morphisms are localized in space-like separated regions. And the second statement has to do with the product of intertwiners. If T is an intertwiner between rho and rho tilde, S is an intertwiner between sigma and sigma tilde. Rho is localized in O1, rho tilde in O tilde 1, sigma in O2, sigma tilde in O2 tilde, and O1 is space-like to O tilde 1, and O2 is space-like to O tilde 2. Then also the product of intertwiners is commutative. And since this is the key lemma which allows to define the statistics of sectors, I would like to give an hint of the proof. It's not going to fit here. Just to give you a flavor of what kind of arguments one uses in this setting. So for the first statement, we have two morphisms, one localized here and one localized here, space-like separated. And I can take an element A in A of O, which will be somewhere here. Then I can take another region O3 here and another region O4 here, in such a way that these two are inside a double cone of 5, and these two are inside a double cone of 6, which are space-like separated. So 5 is space-like separated from 6. Then I can take a morphism rho 3, which is equivalent to rho 1 and is localized here. So rho 3, and I have a unitary intertwiner between the two. And I can take a morphism rho 4 localized here. And I have a morphism U24 between the two. From what I said before, this will be contained in A over 5, and this will be contained in A over 6. So now if I compute rho 1, rho 2 of A, I can write this. So U13 is an intertwiner here. So this is U13 star. Then I have to put rho 3. Then rho 2, I can write it as U24 star times rho 4. But then rho 4 of A is equal to A because A is here, and rho 4 is space-like separated, so this is A. And U24 is localized here, and rho 3 is localized here, so also rho 3 of U24 is U24, and rho 3 of U24 star is U24 star. So in the end, this is U13 star, U24 star, A, U24, U13. But then one can also interchange U13 and U24 because they are space-like separated. And then by doing the computation in the backward direction, you get rho 2, rho 1. Okay. So this proves the first statement. Concerning the second one, the situation. So, let us consider first the particular case in which we have O1 here, O1 tilde here, a big double cone O1 hat that contains them, which is space-like separated by some other double cone which contains O2 and O2 tilde. In this case, it's a simple computation to verify that T cross S is equal to S cross T. It's a computation. Now, in the general case, we will have O2 here, space-like separated from O1. And take another O3, which is also separated from O1. And take a rho 3, which is equivalent to sigma. So there will be a unitary operator U between rho 3 and sigma. Um, I should have used different notation, but anyway. So I had sigma here. Then I have an intertwiner S between sigma and sigma tilde. If I take S, I call S3. S goes from sigma to sigma. S3 is US. Yes. And I compute T times S3. Then T times S3 is T rho US. But U is localized here, and O1 is localized here. So this is TU rho S. And T is localized S is localized. Yes, you can also interchange U and T because they are also space-like. And if you do the computation in the opposite direction, so this is U T times S, and if you interchange them and do the same computation, you also find U S times T. So this means if I do this move, the two sides of the equality change by the same amount. So if I'm in the general situation in which I have O2 here, O2 tilde here, then O1 here, O1 tilde here, by doing a sequence of this kind of moves, I can move O2, this was already, okay. I can move O2 in such a way that it is also space-like to O tilde 1. So I can move O2 here to a new O2 by doing a sequence of these moves in which I always stay in the space-like complement of O1. And then I can do also the same for O1. I can also move O1 here by staying in the space-like complement of the new O2. So I can move O1 here in such a way that in the end I am in the same situation as here. Since for each of these moves, the two sides of the equality change by the same amount, and in the final situation they are the same also at the beginning. So this is the idea of the proof, and the important point is that in order to be able to do this homotopy, you need at least two spatial dimensions. You cannot do it in one spatial dimension. And this is at the basis of the definition of statistic of a sector. So, because if I now take several morphisms, all equivalent to a given morphism, localized in space-like separated regions. So this will be in delta 1, this will be in delta n, and these are mutually space-like separated. And I take intertwiners UK between rho k and rho. By omega naught, I indicate the vacuum state. And I have all the states in which I take omega naught composed with all these morphisms in any given order. So pi is here a permutation. And this is given by u pi 1 cross u pi n star omega rho to the n of a u pi 1 cross u pi n star omega. So all these states are these are all states which are vector states in this representation rho to the n, and they are induced by these vectors. Psi pi, u pi 1, u pi n star omega. So for any permutation, I have a vector which induces a state in the representation rho to the n. But since these are localized in space-like separated region, all these states are the same because the morphisms commute, as we have seen. So all these states are actually the same state. So I have different vectors which induce the same state. And these vectors I can define I can take these operators, and these operators give a representation of the permutation group. Such that is independent of the choices that we have made, so the choices of rho 1, rho n, u1, un, by the lemma that I have proven. This representation lives in the commutant of rho to the n, rho to the na, and intertwines transforms among themselves all these vectors. So epsilon rho n pi applied to psi pi prime is psi pi pi prime. So this representation of the permutation group has all the properties that usually one has when one permutes the arguments of a wave function of n particles. Is analogous to the permutation of arguments of a wave function. Yes.
Product among the unitaries, the usual products of unitary operators.
Yes, just these are intertwiners, so you can. It's
yeah, but it's not the product.
No. This is the usual product, and this is the cross product. We have two operations in between intertwiners. So they can be composed as unitary operators, and you have the cross operation, and you use both.
Sorry, what do you mean you use the same
So
symbol?
this is the ordinary product.
Ah, no, okay.
This is the ordinary product, and the cross is this the other one. Yes. Okay. So we have this representation of the permutation group inside any uh, composition of n-fold composition of a sector with itself. And one can analyze the kind of representation that one gets. And okay, maybe I just give you the result. So uh, there is something called the left inverse uh, of a morphism. And if you compute the left inverse on epsilon rho, which is epsilon rho is just the case in which you take two sectors and you take the transposition. You take the representation of the symmetric group of two elements and you take the transposition. This can, if rho is irreducible, this can only be multiple of the identity, and this lambda can only be one over an integer, one over a natural number, which only depends on the equivalence class of rho, so only on the sector. And in this case, one says that this representation is parabose of order D. Well, this means that if you do the decomposition of this representation into reducible subrepresentations, the representations of the reducible representation of the permutation group are classified by Young tableaus. And parabose means that only Young tableaus in which you have at most D rows appear. And if you have at most D rows means that the representation cannot be antisymmetric in more than D positions, D places. So it's a generalization of Bose statistic in which you don't have too much antisymmetry, essentially. The other possibility is that lambda is minus 1 over an integer, a natural number. In this case, it is parafermi over D, which means that you have Young tableaus with at most D columns, so the wave function cannot be too much symmetric. And there is the exceptional case in which lambda is 0, which is called infinite statistics. Where you can have any possible reducible representation appearing. But this is, of course, less physical, and in fact, it can be excluded by assuming that the sector has translation covariance with spectrum condition and massive particles. So in some sense, it's pathological. So we didn't use covariance and positivity of the energy up to now. If you add the assumption that in the sector you have positivity of the energy, this can be excluded. And then, so finally, one also has a notion of conjugate sector. So for each row irreducible, there exists a unique rho bar, which is also irreducible, such that rho bar and rho contain the vacuum representation. In general, rho bar rho will not be reducible, but if you decompose them into irreducible subrepresentation, it contains once the vacuum representation, so you interpret this as the conjugate charge with respect to rho, so it can annihilate into the vacuum. So the moral is that all the structure that one usually expects from quantum field theory for the charges is reflected in this set of localizable morphisms. You have composition, you have statistic, and you have your statistic, and you have conjugate sectors. Okay, maybe we take a 5 minutes break.
Yeah. Any question for Gerardo?
Yes, I'd like to ask a question.
Yes.
In Lagrangian and Gaussian-Wightman field theory, we usually start with some set of fundamental fields, which are not necessarily observables, and you construct observables.
Yes.
Taking products, combinations. In that operation, you have to solve problems because these objects are singular.
Yes, of course.
So is there, so here you have the opposite, you move in
opposite direction. I assume that I have everything.
Okay. Do you have similar problems here? So I don't see these problems here in this.
No, actually, in this axiomatic framework, you assume that that problem has have been solved, and so you assume that you have given.
But you cannot see an observable as a combination of some fundamental objects. No.
So not in a specific way, but so what I will discuss after is the Doppler-Roberts reconstruction, in which you starting from this structure, you get back to the structure that we had at the beginning. So from the observable algebra, you can construct a field algebra from which the observable algebra can be selected as the fixed point under the action of a global gauge group. So in some sense, that's the answer, but of course you don't have some specific formulas. But you know that all observables are obtained by fixed points of.
And if you want to
But besides some engage invariant combinations of the field.
yes. And if you want to construct scattering matrix, so in the standard case,
In this framework, you can use Agruel scattering theory. If you have to assume that you have massive spectrum, and
for observable not for
you can start from the observable, construct the charges fields, and apply.
and then
The charges fields satisfy all the usual assumptions, so they are both Fermi. You have translation covariant, Poincare covariance, and you can apply the usual machinery.
Another question? Okay, so let's reconvene in 5 minutes. Okay.
È 0 per quello che andava dallo spazio di vuoto a quello con dentro una particella, no? E qua scriviamo il 0 star, ok, che quindi
Forse si devo mettere qua, sì, hai ragione. Mi sono scordato.
qua pi
Sì,
non è P0.
No, è qua.
Perché così adesso questo va in H0 e posso controllare di nuovo. Ok. Va bene, ma questa nozione qua non è molto chiara. Cioè questa è tipo l'interplane tra rappresentazioni solide. Però fisicamente non è quello che trasporta, se lo posso pensare come
quello che trasporta una carica da questo a questo.
Ma e quindi perché quando io adesso vado a come serve, che differenza c'è tra T per S e T processi, come operazioni.
E T per S porta la carica pro nella carica sigma e poi la carica sigma nella carica tau.
Ok.
Invece T cross S
Mm.
porta un prodotto di cariche in un prodotto di cariche.
E quindi questo
Cioè una
senso-
composizione di cariche, cioè esiste solo quando sai fare una composizione di cariche. Porta una carica composta,
Ok.
cioè,
Ed è per questo, cioè, questo qua sarebbe quello che trasporta sigma e sigma prima, poi vi aggiungo la carica rho e
esatto,
poi t mi sposta anche quello.
esatto,
E però e quando io vado a invertirle, in generale poi ci sarà un sigma invece
esatto.
che essere un rho, ok? E quindi quando li scambio in qualche modo io sto dicendo che, visto che ho in mezzo una rappresentazione diversa, io come faccio a scambiarli?
Però appunto vale in questo caso in cui c'hai commutatività.
Mm,
C'hai questa situazione, la sorgente, il target del primo e la sorgente del target del secondo.
non si
Cioè la
parla.
sorgente del primo e la sorgente del secondo, il target del primo e il target del secondo sono mutuamente spazialmente
Esatto,
separati.
sì, però dico, ok, cioè, fisicamente mi aspetto che questa cosa sia vera, però dico, cioè proprio, qua tu hai detto, tipo, si fa un conto e si vede che in questa situazione qua, questa cosa è vera.
Sì, in questa situazione
Però, cioè, nel
il
mezzo
conto è
abbiamo,
semplice, no?
però nel mezzo abbiamo una
Sì,
cioè,
però
quindi come faccio a devo inserire un operatore che mi trasformerà in sigma.
Stai qua in questa situazione, no? Qua ho uno, qua ho uno tilde, e c'è il t che va da qua a qua, chiamiamolo t1 perché portano un qui c'hai io 2, qua c'hai 2 tilde, e c'hai t2 qui, no? Allora, quindi t1 per t2 è questo qua ci sarà ρ1, qua ρ1 tilde, quindi questo è ρ1 t2. Ma t2 sta qui, ρ1 sta qui, quindi questo qua è t1 t2.
Adesso proprio come operatore unitario.
Beh, questi non sono unità in generale, sono operatori, possono anche non essere unità.
Cioè,
I riflettori possono essere operatori anche non unitari.
però cioè, fisicamente non aspetto che siano unitari.
Fisicamente c'è il senso che tu puoi avere questi non sono tutti riducibili, quindi potresti avere un row è una somma diretta di riducibili e c'è un unitario descrivere il fatto che un altro segno riducibile è equivalente a uno dei dei sommandi riducibili, no? Cose del genere.
Ah, però quindi cioè, quando io lo penso questa operazione di trasporto, cioè la devo pensare come le inserisco in un sottosettore.
Se T non è unitario, sì.
Cioè stanno nella stessa dimensione, però lo posso scegliere unitario. E adesso, quindi tu dici, io adesso scambio.
Adesso li posso scambiare perché uno sta qua e l'altro sta qua, quindi questo è il tipo di 1. E adesso qua posso mettere lo 2, perché T1 sta qua e lo 2 sta qua. Quindi questo viene T2 e lo 2. Lo 1 è sparito qui perché T2 era localizzato qua e lo 1 qua. E quindi uno
Quando li scambio spero.
no, qui li scambiamo. Questo qui è uguale a T2.
Ma io qua non sto inserendo una carica qua, adesso che facendo questa cosa.
Però diciamo, non la vede perché sono spazialmente separati.
Ho capito che non la vedo, però io dico se adesso sto dicendo che i vettori sono spazi discrete, se io metto il vuoto qua, quello che mi sta dicendo
Questo è il fatto che in questi settori c'è l'ODA è uguale a però non nel complemento spaziale. Vuol dire, ho delle rappresentazioni che sono uguali al vuoto fuori da una certa distanza.
ho capito, quindi c'è. Perché di fatto cioè, noi
Cioè, qui
stiamo sempre
un'operazione
siamo
in una
sempre
zona in cui che non comunica con.
quindi in qualche modo queste operazioni qua vanno sempre pensate come testate fuori dal doppio cono cioè, in cui sto lavorando in qualche modo.
Cioè, queste sono operazioni localizzate, no? Questi operatori rappresentano operazioni localizzate. Se io faccio un'operazione localizzata in una regione spazialmente separata da dove è localizzata la carica, la è come se la mettessi sul vuoto.
Quindi è come se la fosse sul vuoto, d'accordo, però dico, cioè, se io vado a guardare globalmente quello che succede, è diverso se faccio questa operazione sul vuoto, è non diverso nel senso che è un'operazione diversa, diversa, ma lo stato che ottengo sarà diverso. Cioè, ho capito che io posso spostare una carica da qua a qua in vede questa, però se io sto facendo questa operazione su vuoto, lo stato che ottengo alla fine sarà diverso se qua non ho messo niente, se qua ho messo qualcosa.
Sì, certo, però sono stati che coincidono sull'algebra.
Ok, quindi in qualche modo io devo sempre pensare queste operazioni sul commutante di dove sto generando. Ah, ok, va bene. Ok, grazie mille.
Such a guy just flies to England and then
Yeah, but I don't know. If I book, I just jump.
So this was the general situation when you only consider DHR sectors, but as we said before, you, sorry, you don't expect that you don't expect that they exhaust all possibilities also in massive theories. Also in massive theories, one could have sectors which are not charges which do not behave as DHR charges. And the situation was analyzed by Buchholz and Fredenhagen in 82. they start from a representation pi, let's say reducible, in which you can implement translation, so such that there exists a representation of the translations on the space of the representation pi, such that u pi a pi b, capital A u pi a star equals pi alpha a of capital A. So that's a representation of the translation group in the space of the representation pi, which intertwines the action of the translation in the vacuum representation, and such that the spectrum of the generators of translations is contained in a set of this shape. So you have a discrete mass shell and then a continuum which is separated by a gap from the mass shell. So this means in this representation you have particles with a sharp mass, m. So in this sense, this is a purely massive representation. Then the first statement is that if you move to space like infinity, you get multiples of the identity, and this omega naught is a vacuum state, a pure vacuum state. So it's a state, which means it's a state in which, if you do the GNS representation, you get a representation of the translations in which there is an invariant vector, and the representation is irreducible. And second, for all space-like cone, well, a space-like cone is a region of this shape. You fix an apex, you fix a double cone which is space-like with respect to this apex, and you take the cone generated by the space-like cone generated by these two objects. And for any such space-like cone, the restriction of the representation to the algebra of the space-like complement of this double cone is unitarily equivalent to the vacuum representation obtained from this vacuum. So this means you have this, in these sectors, the charges can be localized in this kind of regions, and the direction in which you have to remove from the sphere in order to have equivalence, it's not important. It's just important that you have some direction that you remove, and this you can interpret as the string, the string flux attached to a gauge charge. So in any massive theory, you always can localize charges in the space like in such a region, in such a space like cone. And these are called BF sectors or topological sectors. And for them, one can do an analysis which is very similar to the DHR analysis. You can always you can again pass from a representation to a row of A, which is sorry, there was a misprint before. Before I wrote like that before, but actually there was you had to put a pi there too in order to define row. That's the HR. Now you can do the same. You define row A as VC VC star pi A VC for BF charges, where VC is a unitary which intertwines the vacuum representation and the BF sector. This is again localizable if A is space-like to the cone, then row A is equal A. So this is again localizable. It's not a morphism actually in general because the von Neumann algebra generated by the space-like complement of a double cone is in general not inside the quasi-local algebra, but using some, so I'm not going into details, but so using some trick, using so if I want, so I need to define the composition, and the composition can be defined by, so I have a row 1 localized here, I have an element A localized here, and I have a row 2 localized in some other space like cone. I can always choose an auxiliary space like cone here and a row 3 equivalent to row 1, to row 2, and I can use this auxiliary row 3 to define the product of row 1 and row 2, because this row 3 acts trivially on things that are here, so it's rather easy. So using this kind of trick, one can define the product, so the composition of this kind of BF sectors, and then one can do the same analysis, essentially the same analysis of composition, statistics, and all the results are obtained in the same way. So it's also this situation can be analyzed in the same way. And and then, as I was saying before, answering to the question, one cannot, yes.
Sorry, but what is the problem with the massless theory?
So with massless theories, the problem is that so when you have a double cone, so the problem is for electric charge, not specifically with massless theories. The problem is that if you have an electric charge localized here in this double cone, you can measure it in a sphere in a sphere which is contained in no prime because you can because of Gauss law. So you measure the electric flux on this large sphere, and this tells you what's the charge inside. So you cannot expect that a sector which describes a charge localized here can be equivalent to the vacuum in this region. That's the problem. Okay. You could expect that it satisfies this, but this is not also the case. I will discuss this afterwards. So, electric charges cannot also be localized in space like cones. It's even worse than that. Okay, maybe I will say something afterwards. So for the moment, instead, I wanted to explain how one can recover the structure that we had at the beginning, so the field net and the gauge group from the knowledge of from the structure of the HR sectors. In order to understand that, one has to, so it's a complicated construction, but so to grasp it a little bit, let's take a step back and go back to the situation that we had at the beginning. So when we have a field net and we have a global, we know the global gauge group, and suppose that so F is a field net, and I suppose that the global gauge group is a subgroup of SUD, called subgroup of SUD. Then in this situation, one can show that f of O is generated by the observables and by elements psi1, psi d belonging to f of O, which are a so-called multiplet of orthogonal isometries of support 1, which means that psi j star psi k is delta jk times the identity. Sum over j going from 1 to d of psi j star is equal to 1. And if beta g is the action of the gauge group on the fields, beta g applied to psi j is sum over k g jk. G is an element of SUD times psi k. So these operators transform under this representation, the fundamental representation of the group G. So this is called the multiplet of orthogonal isometries of support 1. So in this situation, the field net is generated by the observable algebras and these D operators. And these operators are obtained by considering intertwiners between the vacuum sector and the charged sectors. So since G is contained in SUD, this means that all the representations of G, all the reducible representations of G are a sub-representation of a multiple of the fundamental representation, and so it is sufficient to consider so the different superselection coherent subspaces are labeled by the representations, the reducible representations of G, so it's sufficient to consider the subspace labeled by the fundamental representation. You can, looking at how the fields intertwine the vacuum with that space, you can construct these specific fields. And now, so one is the converse problem is given, moreover, the localized endomorphism associated to this fundamental representation of the gauge group is implemented by this operator psi j by this formula. Rho of A is given by that formula in this case. And so the set H, the span of these psi j's is actually a finite dimensional Hilbert space inside the algebra f of O. And the scalar product psi prime is given by psi star psi prime. So this is psi star psi prime is always a multiple of the identity, and the coefficient of the identity defines the scalar product in this space. So this is a Hilbert space. And for all psi inside this Hilbert space, psi A equals rho A psi. by that formula. Psi star. No, sorry. Psi. It's psi. So, so one has the converse problem. So one starts from the observable algebra and wants to reconstruct such a structure. So one starts from A, the observable algebra, and assumes that there exists localizable, irreducible, localizable, transportable nomorphism, which generates the superselection structure in the sense that all the other irreducible morphisms are sub-representations of multiples of powers of this. So any other is contained in row to the n, which is what happens here, which is what happens in this situation. So since in this situation f of O is generated by A of O and these multiplets, one can consider the Kunz algebra, which is precisely the C-star algebra generated by these relations. One can show that there is a unique C-star algebra which is generated by the elements which satisfy that relations. And so the first guess would be, okay, I take the tensor product. Since I want that f is generated by A and by these multiplets, I try to take the tensor product. But this is wrong because we want that. So OD will on OD we have an action of SUD by this formula. So there are invariant elements inside here, and they must be identified with observables. The invariant elements must be observable. So this cannot be because there are invariant elements here which are not here. And so one has to identify those things, and the way to identify them is to show that there exists a map mu from A to the invariant part of the Kunz algebra. These are the invariants of the Kunz algebra, which satisfies certain properties. And then one can define f as, so this is not actually f, this is f tilde, as the module tensor product of A with OD with respect to this mu, with respect to this action mu, which means that if I have I should have written it the other way around. It's better. Only SUD to A tensor CX, where C is an invariant element of the Kunz algebra. This is equal to A mu C tensor product X. In this way, I have identified the invariant elements in the Kunz algebra with elements in the observable algebra. So, and the conditions that this map has to satisfy are those that guarantee that you can do this operation. In this way, this is just a vector space, but you need an algebra, so you need to define a product between elements of this, and so you can define product. So you need to know how to commute fields and observables, and one one relation that gives you this commutational relation is this one. Then you need also a relation in which you have the stars, but so this also can be obtained from the previous situation. So you can also define a product, but this is not yet the end, because now we have identified the invariant part of OD under the whole group SUD with elements in A, but we need to identify the invariant part under the group G, which is a subgroup of SUD in general, and we don't know G. We just know SUD because we know D, and D is a property of the morphism from which I started. This is the statistical dimension of the morphism. So we know D, we know SUD, but we don't know G. But then one can show that there is an ideal in this algebra which kills. So this algebra as a center, and you can take an ideal which kills the center, and in the end you obtain that F is F tilde divided by this center, by this ideal. And in this way, you identify only the invariant elements of G with elements of A. And G then is the group of automorphisms of F which leave the observables invariant. So this is the sketch of the construction in this particular case, in which you have a special morphism which generates all the superselection structure, but then you have to one has to generalize to a general case in which there are many morphisms, but so this can be done. And in the end, what one gets is this Toglier-Roberts reconstruction theorem. It says that there exists a field net with both Fermi commutation relations. So you have a grading of the algebra, of the local algebras, in a Fermi part and a Bose part, and two fields from the two elements from the Bose part which are space-like separated commute, two elements from the Fermi part which are space-like separated anti-commute, and all Bose elements commute with all all the Fermi elements at space-like separation. So these are normal commutation relations. There exists a V. There exists actually a G compact group, and the representation on the Hilbert space on which the field net lives, such that A of O is the invariant part of G of the field net. If rho is a morphism which is localized in O, irreducible, and parabose or parafermi of order D, then rho is implemented by a multiplet C1, C1 psi D, which are both fields belonging to of F, both or Fermi, like in the formula that I wrote before. So rho of A is sum of psi j A psi j star. This is the meaning of implemented, which transform under irreducible representation of G of dimension D. So the statistical dimension of rho is the dimension of the representation of the group G under which this field operator transform. F of O is generated by A of O and all those multiplets. And finally, F and G are unique. So we go back to the situation from which we started. So only the knowledge of the observables allows you to completely reconstruct the field theoretical situation. You have fields satisfying normal commutation relations, which create all the DHR charges from the vacuum in this sense. And there is a one-to-one correspondence between the DHR sectors, so the classes, the equivalence classes of localizable and transportable morphisms, and with finite statistics. Sorry, I forgot, with finite statistics, and the irreducible representations of the group G, which is what you expect in quantum field theory. For all of this, the fact that you have a permutation symmetry and not a braid group symmetry is essential. So you cannot do this in lower dimension when you don't have a representation of the symmetric group of the permutation group, but only of the braid group. And this can also be extended to BF sectors. So also for BF sectors, you obtain a similar structure in which the fields are localized in space like cones instead of double cones. But for the rest, everything works in the same way. Now, as maybe a final comment, what happens in the case of you had a question?
Yes. No. What is the abstraction when we have what is the abstraction of doing this?
When we don't have permutation symmetry. The abstraction is that when you have a representation, the category of representation of a compact group is permutation symmetric. So you don't expect. So when you take the tensor product of representations, you always have a permutation, a representation of the permutation group in the n-fold tensor product of representation of the group. So you don't expect, since there's a one-to-one correspondence. So another way of expressing this theorem is that the localizable morphisms form a symmetric category, symmetric tensor category, like the category of the representations of a compact group. And you can view this theorem, so this theorem can be reformulated by saying that a category, a symmetric tensor category is the abstract dual of a compact group. So once you have a symmetric tensor category, it is always the category of representation of some compact group. So if you don't have symmetry, you don't expect to find a compact group. You expect to find some more general symmetry like quantum groups, but this is not known. What happens in the case of electric charges? So for electric charges, one can, so if I have a representation in which there are electric charges, I can define the asymptotic distribution of electric flux, which is n is a unit vector, and is limit for r going to infinity of, so that is a r cube. That's the electric field. I can define this quantity, which is the distribution of the electric flux around a very large sphere. So since we are going to space like infinity, this object commutes with all observables. So in a reducible representation, this must be a multiple of the identity. But this means that if you have two representations which have different for which this quantity differs, they cannot be equivalent. So in particular, you can have a representation in which this quantity is localized along some space like cone, and another one which is localized along another space like cone, and this cannot be equivalent. So the electric charge cannot even be localized in a space like cone, because there you need to be able to change space like cone. So BF sectors cannot describe electric charges. And actually, the situation is even worse than that, because, of course, you have continuously many distributions which give rise to which correspond to the same charge, because the charge is given by the integral of the distribution along a sphere. So the electric charge is the integral of the flux because of Gauss law. So you can have continuously many inequivalent representations which describe the same electric charge, which is of course rather bad. So this means that one needs a coarser equivalence relation with respect to unitary equivalence. Unitary equivalence is to find to be able to describe electric charges. And so the main observation by Buchholz and Roberts, this is in 2014, is that one should not do the analysis on Minkowski, but one should do the analysis in some forward light cone. Because if I am in a forward light cone, every massless particle which is created in the past of the cone will never enter into the cone. So you expect that you don't see these observables inside the cone, because these observables are these elements are obtained by considering the photons. These observables are obtained by considering the electric field. Instead, massive particle will always in the end, and any massive particle which is created somewhere here, in the end will enter the cone. And the electric charge is carried by massive particles physically. So electrons are massive. So what one expects is that by restricting to the cone, one can only see the charges without those soft photons accompanying them with make the representation of Minkowski inequivalent. So they propose this definition of charge classes. And you take a pi representation, a reducible representation such that if you take pi on the algebra of the forward light cone and take the fundamental algebra, this is type 3-1. So this is highly reducible, which means that you are considering a situation in which something escapes. In which if the theory is massive, one can show that this algebra is always BOH, so it's not type 3-1. So type 3-1 is the signal that you have some massless particles. And then one says that pi 1 is in the same charge class. Is in the charge class of pi if pi and pi 1 are unitarial equivalent on the forward light cone. Which is a way of expressing the fact that that all charged particles will eventually enter in the forward light cone. So from the point of view of massive particles, the two representations should be equivalent. And then if I have the forward light cone, I can select a time hyperboloid, and I can define hypercones as the causal completion of cones, hyperbolic cones on this time hyperboloid, which will be regions like that inside the forward light cone. So this is an hypercone. And then they look at representations. So better, they look at charge classes in which you can localize all the representations in some hypercone, like that. So they require that for each hypercone, there exists a sigma c into the charge class, such that sigma c is localized in C, in the sense that we saw before for the other kind of sectors, and then it's transportable and so on, and transportable. And the reason for doing this is that you expect that. So this means I'm creating a charge in this hypercone by taking two opposite charges and taking one at space like infinity along the hyperboloid. And doing this, one expects that the soft photons that are created in this operation are not visible inside the forward cone. So the sigma c, the sigma c is only acts on the forward cone. Is a map from the forward cone to its fundamental algebra. And selecting this particular class of representation, they show that one can do again all the machinery, all the analysis of sectors, just as for Doppler Roberts or BF sectors. So again, one has composition, symmetry, and so on. So also by this observation of restricting to the forward light cone, one is able to again do the sector analysis also for electric charges. Okay, I think I will stop here.
There are the night vectors in question. Curiosity from
Yes.
It seems in this construction that you try to avoid soft photons.
Yes, exactly. Yes.
Instead of the conventional one, you put them. Because the scattering amplitude is divergent without.
Yes, here the problem is that if you take into account the distribution of soft photons, you are not going to obtain equivalent representations, even if you have the same charge.
I understand.
Yes,
Mathematical reason, but I was trying to understand.
yes, I see what you mean.
And I have also another question. And this is
So in a sense, doing this, so this block Nordsec thing. So this it's an infrared regularization in some sense.
there is also physics behind that.
Yes, of course. One says I cannot measure. Yes, I cannot measure. Yes, of course. In some sense, you can look at the forward light cone as an infrared regularization. You cut away space like infinity in some geometrical. In this sense, it's.
And what about Lorentz invariance in this setting?
So you can start from Lorentz symmetry, a subsymmetry. So you have a subgroup leaving the cone invariant, and then you show that you can always extend to the full Lorentz group.
Keep Lorentz.
Yes.
Because I remember that in the past there was a problem with Lorentz symmetry in the charges.
Yes. Now yes, it's solved. Yes.
Okay, thank you.
Question? Okay, if not, let's thank Gerardo again.